So if ionization energy is removing electrons from neutral atoms to form cations, electron affinity is adding electrons to neutral atoms or to ions to form anions. And it's defined in this way. The electron affinity, which is given the symbol EA, is the energy change when an electron is added to a gaseous atom or ion. So an example would be chlorine, the chlorine atom plus an electron to form the chloride anion. And the energy change associated with that process is defined as the electron affinity for chlorine. Now, one thing we must highlight here, it may seem as though electron affinity is the opposite process of ionization energy, but the two are not opposites. In one case, we start out with electron affinity, we start out with a neutral atom and we add an electron to go to an anion. The reverse process of that would be starting with an anion and removing an electron to go to a neutral atom. But that's not the same as ionization, as ionization energy. Ionization energy starts with the neutral atom and removes an electron to get to a cation. The reverse of that process would be adding an electron to a cation to form a neutral atom, which is not the same as electron affinity. So please make sure that you get those two distinct from each other. The ionization energy is not simply the opposite sign of the electron affinity. Those two are two different processes. Now that we've got that out of the way, electron affinities aren't generally negative values. We're adding an electron to an atom, so generally that process gives off energy. Now there are some exceptions to that, however. If we have an atom that has a filled or half-filled subshell, then adding another electron to that isn't a favorable process because that electron either has to go into a new set of orbitals all by itself, or it has to pair up with an orbital breaking the symmetry of the half-filled subshell. So if you were adding an electron to a filled subshell or a half-filled subshell, those processes are not negative. We would consider them not favorable. Those would be positive energy values. But otherwise, electron affinities are generally negative values. And there are trends to electron affinities, just like there are trends to ionization energies, and there are some similarities. But what we'll point out from this periodic table is that they do tend to increase as we go left to right across the periodic table, or at least increase in terms of becoming more negative, similar to the way that ionization energies became more positive as you go left to right across the periodic table. But you'll notice some gaps. So at the very end of the periodic table, the noble gases, those have non-negative or positive values for their electron affinities. And the reason for that is because we have a filled, not just filled subshells, but a filled shell. The noble gases, all of their orbitals are filled. So adding another electron to that has to go not only into a new subshell or into a new orbital, but into an entirely new energy level, which is not very favorable. And so the value for that is positive. Same thing is occurring now, and just in terms of subshells, when we look at the elements at the end of the D block or at the end of the S block as well. Now, with these, or even one thing to point out, the half-filled cases, so nitrogen and phosphorus, arsenic, etc., half-filled for the P subshell, those are lower values than the other ones because it's generally disfavored to add an electron to a half-filled subshell. And the same thing is true for the D block as well. So the trends are similar to ionization energy trends, not equal because of the gaps, but they are similar to those. And the horizontal increase in electron affinity as we go left to right is due, at least in part, due to the increase in effective nuclear charge, just like the ionization energies. If we have a larger effective nuclear charge, then the nucleus is wanting electrons, it's pulling strongly towards it. So if you give it another electron, then that's more favored than an atom that has a lesser effective nuclear charge. So that's electron affinities. Let's take a couple applications of this quickly. So would a neutral potassium atom or a potassium ion have a more negative electron affinity? So we're going to be adding an electron to either K or K+. What we have to look at is, okay, what orbitals are going on here? K has one valence electron. So if you add another electron to it, it's just going to fill the s orbital. K+, however, has given up its valence electron. It now has the same number of electrons as a noble gas. So if we look here, potassium, and go back one row up to argon, then now we're at that case where argon has all of its orbitals and subshells filled. So potassium plus K plus has the electron configuration of argon, and if we add another electron to it, that electron has to go into a whole new energy level all by itself. So that would be very disfavored. So it's going to be more negative to add an electron to just the neutral K atom. Now, multiple electron affinities are also possible, just like ionization energies. You can have the second electron affinity or the third electron affinity. So which of the following elements would have the least negative second electron affinity? So this is the case where we're going to add one electron, and then we're going to add another electron to it after that. So if we look at the electron configurations for each of these, you can write them out. Boron has 3 valence electrons. It has its electron configuration would just be 1s2, 2s2, 2p1. Chlorine has 7 valence electrons, and so it ends up having a noble gas configuration, and then it should be 3p2, 3p5. Selenium it's in the oxygen column, so it has 6 valence electrons. And nickel is over in the metals. And if we look really quickly just where it appears, nickel is here. And so it has, of its d electrons, it has 8 d electrons. And so we're looking at each of these cases and what would happen if I add 2 electrons to it. So nickel, if I add 2 electrons to it, I'd simply get to zinc. So I've actually filled all of the d subshell at that point. And that's good. So adding the second electron, there's no problem with that. Boron, if I add 2 electrons to it, it just goes to have the same number of electrons as nitrogen. You've half filled the p subshell, so there's nothing wrong with that. Chlorine, on the other hand, chlorine is here. If you add 2 electrons to it, well, what happens? The first electron that you add goes to complete the p subshell for chlorine, and then it has the same electron configuration as argon. So adding the second electron to it will now bump that electron all the way into a new energy level to get up to the 4s energy level. That electron has to go into an orbital all by itself at a new energy level. That's going to be disfavored. So the second electron affinity is not favorable for chlorine. So that would be positive. Selenium, however, adding 2 electrons to that simply completes its p orbital set. So that's also completely fine. We would expect the second electron affinity to be negative for selenium. So I hope that that helps in terms of how we work through electron affinities and how it sort of relates to ionization energy and how it's different.